Seeing data, seeing ratios in data visuals, presentation 102. We'll be thinking about ratios, data displays, and comparing data sets using ratios. Our goals are to use what we have already done, comparing and contrasting bar graphs with histograms in previous lessons and assessments. Today, we are going to use histograms and other data visuals to make sense of the most recent data from our IXL diagnostic data. I encourage you all to play with your data sets from watching your movies or noticing things in your life, like your data cards, to analyze the data that you've collected using ratios, measures of center, and measures of spread. I hope that these lessons are guiding you and helping you think. Please do not think that you have to complete every page in these lessons. These are sort of sub-plans for you all. Do what you can, do what you're interested in, dig deep or spread yourself across the whole thing. Try to get everything done a little bit or try to do one thing really well. Either way is perfect. Okay. The overall level of all students on our team who had enough time in the diagnostic arena, so that is a huge condition. This does not represent our whole team. It only represents those students who have put enough time in the diagnostic arena to be considered for the algorithm to have enough data to make a judgment call, to make a statistical call. So this is something we're talking about with ratios, that a lot of algorithms use ratios. I'm not sure if IXLs does, but if it does, often statistics and diagnostic tools will use this idea of large numbers. If we can have a student answer enough questions, the law of large numbers tells us that we can use that data to get a likely level. So these overall levels for you all in mathematics are likely, are probable, based on the algorithm and the diagnostic tool. So given that sort of context is so important with statistics. What do we see here? Please note that it's important you all remember the reason I'm posting the the December data in this post is because it's really cool to see how far we've come. So if you go back to December, compare and contrast histograms and bar graphs, this was the data from your IXL diagnostic arena in January. And if you notice, our overall data set had a range from 50 to 700-ish, 675. And now we're at from 80 minimum to 690. So the overall range is pretty much the same. What's changed is that we only had about, I think, 25. So 4 plus 3 is 7 plus 3 is 10, 11, 12, 13, 15, 17, 19, 20, 22, 23, 24, 25. That's what I thought. 25 students were represented. So in a month, something cool that we already noticed is that the number of students, this is a ratio, the number of students on our team who had spent enough time in the IXL diagnostic has doubled. When that number has doubled, though, it's also important to put it in reference of the whole group. So while that number is doubled, it's still not everyone. It's still 2/3 ratio for every 3 students on our team, only typically 2 have been in the IXL diagnostic enough. We have close to 80 students working with us in this math class. So ratios, comparing and contrasting data. Let's take a look at the mean and median. In December, the overall math mean and median for students who had enough time in the diagnostic from our 6 South team was around 390. Both mean and median were very close, so this data is pretty symmetric. The data looks less symmetric to me now. It looks a little bit skewed left. It looks like more of the data is centered to the right of the The orange line is the mean, 418. So we went from 390 to 418, and the median is even higher. So that's what I was saying. The median's even higher because the modes here, we don't know exactly. Oh, no, we do. No, we don't. I didn't calculate the modes. But in our bin sizes, you can see the highest frequency of student scores is from like 400 level-ish to the middle of 5th grade level. So that's nice. In a month, we've gotten more students, so we're getting more accurate data. Our denominators are getting bigger, so our data is getting more accurate, and we can talk about that more as we get stronger and more confident in thinking about ratios and statistics. But this law of large numbers really ties ratios to statistics well. Anyway, so I don't know, what do you all think? What do you wonder? What do you notice? And you can jump on over to your student worksheets and say, what do you notice? What do you wonder? And what's going on in this graph for our current overall scores? So I'm going to jump over here. What do I notice? I notice that in a month's time, the number of students on our team who have spent enough time in the IXL diagnostic arena has doubled. This makes our means and mean absolute deviations more representative of our entire team, but not yet truly representative of our entire team. And we can get into that more, but from my knowledge base, I know that this is a pretty biased sample because it's just only the students who conveniently have had enough time to get into the diagnostic and put a full effort in. So until we get everybody, or we have a more random and systematic approach, or maybe not, like a random approach to getting students from our team to represent our group, then until then our sampling method is biased. But anyway, the larger our denominator is, the more accurate our means and mean absolute deviations will be. And I wonder why. So I wonder why the data becomes more accurate when using statistical tools if we have as many people as possible. No, not as many people as possible. I mean, more is better when we have the idea of more is better. So a bigger sample is better than a smaller sample. When you can. But there's limits to being able to just collect everybody's data. Not everybody can always be represented in a data set for various reasons. COVID, huge reason, right? Everyone's absent a lot. So, okay, what's going on in this graph? So here we're going to do a little bit of a deeper dive, and I'll explore some things with you, really focusing on measures of center, spread, and ratios. And then I can try to make videos later with the rest of them, but these are just sort of here for you to explore and to try. So what is going on in this graph? We see that the data is a little bit skewed. The median and the mean have grown further apart. Hi. Than the mean and the median from December. So if you pop back over to the December graph with me really quickly, you'll see that the mean and the median are only 2 apart. They're really bright, so don't look in them, okay? Now the mean and the median, the median is 430, so that's saying that that's our middle point. So half of the students of the 50 students are ready for above middle and above 4th grade level mathematics concepts according to our standards, and then 50% of the students who've taken the IXL diagnostic are ready for mathematics overall that is sort of like around that 4th grade level and below. So that's the median. The mean is telling us 418, 419. And so now that's a difference of 11, which is much bigger than 2. It's multiplied by 5. When we see that the mean and the median are spreading out, it means that the data is getting more skewed. When the mean and the median aren't lining up in the middle anymore, it just means that the data is not that perfectly symmetric. So the data is getting less symmetric. The data is becoming more skewed left. And I know that it's skewed left because it sort of looks like it has a tail to the left, but also because the mean is most susceptible to outliers because it incorporates every value of every data point in the ratio calculation. You sum up all the values and then you divide by the count, right? So that's why when the count gets higher, it should be getting more representative of the reality of the world as we're sort of contextualizing it, because both the numerator and denominator are getting bigger. If you have 100 data points instead of 50, I'm still adding 100 data points in the numerator instead of only adding 50 in the numerator. And so the more data points you have, the less punch the outliers can kind of pull on that total sum. When the numbers are a lot alike, and a lot of them are a lot alike, they hold a lot of power in weight in the calculation. And if there's only one number that's kind of way different than the rest, it's not going to really change the mean so much. But when the data starts to become skewed like this, you get to see how it does impact the mean. And in this case, the mean has kind of dropped below the median. And you see here that the median is this orange line. So I always forget that I have this right here. So the box and whisker plot at the bottom is representing the median. So that's the 50% cut line. And then we also have the quartiles. So breaking the scores into the lowest 25, then the lower upper 25, then the upper lower 25, and then the upper 25. So it's breaking in order where, like, what quartile are you falling in, what percentile. And then with mean, we get to see that the mean's a little bit below the median here. And the mode is to the right of is over here as well. The modes, like, remember, so if you see skewed graphs, mean, median, mode, I'm taking you all here, right? And anytime you Google something, you grab that picture. So I don't know which one you all like, but when it's symmetric, the mean, median, mode are all pretty much on top in the middle. When it's a skewed, so we have a skewed left or a negative skew right now. So the mean dropped, then the median's next, and then the mode's going to be that peak. And that's what we're dealing with now. So say you like this picture, you should grab it, right? And it's from Wikipedia. I can't argue with Wikipedia, to be completely honest. It's helpful just for study skills, as a reference. I mean, it's not something I'm going to reference in a research paper, but it's helpful for me to just get an idea of what's going on. Okay, I don't know why that's not working, and I just want to paste that picture because this is the practice of collecting notes and creating artifacts. Like, you could put any of this into your portfolio and explain it when you're trying to present your student-led conference. Okay, so the data is becoming more skewed left, all right? And so see image below, right? See image from Wikipedia below. Getting into the practice of trying to write, like, sort of in a very concise way. Be precise. And punctuation doesn't matter, but it helps. I mean, punctuation matters, but it's not going to detract you from learning mathematics. Anyway. That was cool. Fireworks. Anyway, we're looking at what is going on in this graph, and because it's skewed left, the mean dropped below the median, and the mode is likely above that for 430, but maybe somewhere in that range. Our interquartile range is 150, and our mean absolute deviation is 100. Our variance is 17,311, and I'll tell more about anybody who's curious about variance. I'll explain that later. But standard deviation is more in the range of the numbers related to like interquartile range and MAD. You see there, it's like 100, 131, 150. That's telling us that that's typically how far the data points are from the center. So they're about 100 points in either direction. So like a grade level and a half, essentially. So the spread in either direction from the center is about a grade level. So we can say this from the students who took this assessment, who are represented in the assessment, it's representing about 2/3 of our team, that most students are ready for mathematics at the level of fourth grade, beginning fourth grade. And that goes about a grade level in each direction. So really it's about third grade to fifth grade, like third grade to fifth and a half, halfway through fifth grade is really our region for, I don't know how to get off that. There it is. So let's say here's the center. So then about 100 below that is here, and 100 above it is about what here. And so that's the region of students who are typical. They're in the middle, and then within that first bound of spread. I'm going to leave it here for you all to explore the rest of them. But I am going to jump down to the next to give you, this one is just trying to show you the bins, what the bins would look like if they went from, instead of 10 bins to 5 bins, because the rest of the graphs are only in chunks of 5 bins. So I did that to help you like kind of see how you would clump it, right? These two would be clumped together. So 2 + 1 is 3. So the width of the bin is deceiving. That's not what's really changing the frequency counts. The frequency counts are going up. But I'm going to skip that one. I'm going to jump down to 5 to look at the MAD. So again, the MAD is 100. The standard deviation is 130, and the IQ or interquartile range is 170. So it's saying that from the center, again, it's about that year or year and a half spread from the middle. So students who have taken data, statistics, and probability enough in the diagnostic arena. What did I use? I used standard deviation here for this one. If you're within this range, okay, so that's helping us with the center and spread. So the middle is considered to be 422, so early fourth grade. And then you're still considered to be amongst your peers if you're at the third grade level or the fifth grade level. Up to the fifth grade level for data stats and probability. If you're beyond that fifth grade level, you're considered to be the upper like percentile or upper, the higher levels than your classmates if you're represented in this data. And then if you're below that third grade level, then you're considered to have a lot more content to sort of get through. But the good thing is that mathematics is all interconnected, so don't feel like you have to like achieve a ton you don't have to climb the ladder. Like we can get you there with like parachutes, and we can work our way up, or like, I don't know, elevators, things like that. So that's the cool thing about math. Anyway, I'm rambling. Some of you probably have just turned this off by now, and you wouldn't be watching anymore if you had. But let's take a look. Here, the mean absolute deviation is getting smaller. So this data set, the fractions data set, is less spread out. So it's more consistent around the middle. So more consistent. Most of you are consistently more focused around this 4.5 grade level, but it's all pretty similar. Like all of your, now the cool thing is, like, we don't know, like, I don't know where, like, if Samantha's in this data set, like, I could be jumping around all, like, I could be really low in numbers and operations and really high in algebraic thinking or something. So this one is the most consistent so far because I see that the mean absolute deviation is 80. So this data is the most consistent around the middle. You can see that it's a way less spread. Look, oh, I don't know why. And then we can say that students, I'm going back to this one, students in the data set are ready for math skills typically from 3rd grade to middle of 5th grade based on this display and the descriptive statistics calculated in Google Sheets. Okay. I really got to end this. I know you all are probably ready for this to be over as well. So this one was the most consistent. You can see here that, look how narrow this center chunk is. That's the mean, and then you're only deviating slightly to the right and left. So that one's very consistent in the center. So go ahead and try to compare and contrast all the 4 data sets. Remember, this one's represented twice in 2 different ways. And take some notes about ratios, measures of center, measures of spread. To get to these links for IXL, just jump onto the PDF, or you can get into IXL and just search up those sort of keywords. Okay, email me with any questions. Thanks for listening and watching. Goodbye.